Hello and welcome to this presentation today. I will be reviewing Flow3D's capabilities with respect to water resource infrastructure modeling. This covers all sorts of topics from municipal wet weather conveyance to flooding to river hydraulics, dams, spillways and fish passages, to settling tanks, aeration tanks, wastewater recovery processes, and then we also have plenty of environmental applications, plumes, overland spills, and so on. So a lot to cover, and in case you don't already know, I should mention that those who registered today will all be sent a link to the slides and to the recording of today's presentation. Feel free to share that link with colleagues, always appreciated. And by the way, we have an amazing audience today with engineers from all over the world, from Egypt to the UK to United States, South America, Saudi Arabia, Canada, New Zealand, Australia, Malaysia, India, and Pakistan, and that's the list I have, but I think I'm missing plenty actually. So welcome everyone. Okay, so instead of going through a list of applications today, I decided to organize topics in terms of physics and models. The idea is that you will all be able to recognize for yourself where these models fit into your own workflow. And if you have any questions, please do not hesitate to email, of course, john.wendelbo@flow3d.com. So I'll talk a lot about hydraulics today, about half the talk, and then move on to additional coupled models that are commonly used for water applications. So for hydraulics, we have basically 3D free surface flows, occasionally shallow water flows, gravity and turbulence, and that really takes care of your hydraulics. For scour and sedimentation, we have a dedicated sediment scour and deposition model which we use. For things like plumes, whether it's thermal plumes or turbidity flows, we have heat transfer, density evaluation, turbulence is very important, and then also sediment scour and occasionally the drift flux model is used for those applications. For things relating to air entrainment or gas bubbles, whether it could be aeration or air entrainment and bulking, those sorts of things, we have an air entrainment and a drift flux model as well. They kind of work together. And we also have a gas particle model, which is new actually in the last release of Flow3D. So I'll show you how that works. We also have some chemistry. We have a chemistry model which we use for that. We have for particulate dynamics, which can mean a lot of things, but let's say for settling tanks, we use the sediment scour and deposition, well, a variation on the sediment scour and deposition model. Sometimes we use the drift flux for things like settling tanks, and then for things that are more kind of mass particles like grit separation chambers, we use the mass particle model. Okay, and then we have a very general, it's called the general moving objects model. So things can move in Flow3D. I'll just show you a couple of things with floating barriers and with mixing, but the model is much more general. I'll show you that, and then we also have catenaries and springs, which can be very useful for certain applications. And then not everything is made out of water, so we have special fluids, and I'll show you some examples of non-Newtonian fluids today. Also granular flows. Okay, so before I start going through all of this, it's probably a good idea to review briefly what kind of modeling platform Flow3D is and where it operates. It's important to understand that Flow3D is a general purpose hydrodynamic nonlinear solver. We solve the full Navier-Stokes equations in 3 dimensions. But what is key for us is that we have focused almost entirely since our inception, almost 40 years ago, on the treatment of free surface problems. I can point out that the founder of the company, Dr. Tony Hurt, was one of the inventors of the famous volume of fluid method. And today, in fact, we deploy a modified proprietary version called TrueVOF. This means that we live in the realm of transients. That's the nature of free surface problems. And it's also worth noting that we use a very simple but very efficient meshing system whereby objects are embedded inside a fixed Cartesian, rectangular mesh instead of having the mesh conform to the object. The net result is that meshing is fairly trivial in Flow3D. Another consequence is that the solver is very efficient because of that. Okay, so the core capability is really the effective treatment of free surfaces. That is a common theme throughout everything we do. And then built on that core, we have all sorts of additional modeling capabilities that are tightly coupled with the free surface solver. These includes, so turbulence, of course, you can't get away with that mostly in environmental flows, but also non-Newtonian fluids, air entrainment, heat transfer, general moving objects, particles, porous media, bubbles and phase change, sediment scour, shallow water cavitation, things like penstock analyses, and then granular flows and Syria. And there's actually a lot more models, but these are the most common ones for water applications. Okay, and then I think it's a fair statement to say that the core strength of the software as a whole is in fact this combination of fairly unique abilities with free surface treatment combined with speed, accuracy, robustness, versatility, and maybe most importantly, maybe simplicity. So it's the kind of combination of all these things that makes the strength of this modeling platform. All right, so if I step back a little, then we can consider all these features. You take free surface flow, additional physics, and look at this through the lens of water infrastructure, and you can see, in fact, how these tools can be very useful across a wide array of applications, from municipal wastewater to dams and spillways, rivers, and environmental. Right. So again, just write this down. Any questions, really don't hesitate. john.wendelbo@flow3d.com. All right, so what does this look like? Some examples. A scour behind a spillway plunge pool on the top left. Water conveyance situation. Right there, next in line, where in fact, in this case, there's so much air entrainment going on and bulking that the entire structure did not work at certain flow rates. So the bulking and the air entrainment, an integral part of the physics here, to the extent, to the point even where flow would back flood through the entrance flume. So that's an interesting case. Here's a dam with a log curtain. Next is a tangential drop shaft structure. This was for a huge project in Indianapolis. A spillway that generates cross waves, a fish passage, a catastrophic dam breach, 1928, St. Francis Dam, turbid effluents right here, and another spillway. These are all ideal applications for Flow3D. Just a selection here, but it gives you kind of a sense of kind of things where we do very well. So I'll go through some kind of different types of hydraulics that we deal with. Start with complex free surfaces, and I differentiate that a little bit from open channel flows because, so for instance, you look at the water here behind the dam, it's fairly quiescent, but that's open channel flow. If you look at the water coming through the spillway or the aeration that happens or the turbulence or the velocities, all that's quite a bit more energetic, and I kind of think of those as a little bit differently from open channel hydraulics. So this is a model from colleagues in Germany, and this is a Flow3D model. And so what do these complex free surfaces look like numerically? So I like to show this example. It's a very basic example then. it's just two jets, and we can look at the flapping of the converging flow in the central nape. This is exactly the kind of flow where the VOF method, volume of fluid method, especially the one-phase version we implement most often, is really invaluable. While this problem is in general quite a difficult proposition to model, in fact in Flow3D, because of the way we do things, it's actually one of the easiest problems you can set up. So a similar problem is the plunge pool, and I'll show you a little later on how this is coupled with sediment and scour model, and we'll see how the scour develops under the pool. Obviously, I should go back. One thing we are interested in here is the detail of the plunge pool, but also the hydraulics, subsequent hydraulics of recirculation regions. All those things are very important for bank erosion. So that's also something you get out of these kinds of simulations. So it's not just the hydraulics right here where the plunge pool impacts the water and hits the bottom there. It's also the additional circulations that happen in this region. Okay. Spillways are obviously perfect candidates. Normally Flow3D is used for discharge analysis as well as super elevation, cross waves within the spillway, those sorts of things. There's actually an entire presentation on this topic which I will point out to you a little later. I'll give you a link. But what we're looking at here, basically there's post-construction addition of a bridge pier, and the question is how does it affect it creates a wave obviously sideways inside the spillway. How does it affect the elevation here of the walls on the side? Is it sufficient? Is it not sufficient? Those sorts of questions. And how does it affect the discharge itself? So a lot of information here. Has a cross section. You can see the flooding of the stilling basin, the detail of the velocity field and of the wave shape, and also these flow patterns right here. So you can apply the same modeling to all sorts of situations, wet tunnels and CSOs in particular. So we can look at the detail of diversion tanks, retention tanks, CSO structures, all in a very detailed and also very transient fashion. So we can really see the behaviors of the structure for given flow rates, different combinations of flows and so on. In this case, it starts off fairly calm, and then we add more fluid. And you can really look at all the details. For instance, you might think that the hydraulic control is this pipe. It's really the elbow here that determines everything, and so on. So the way the flow arrives navigates around this elbow, the influence of the dam here at the end, the weir. When does the structure overflow, under what conditions? All those are fairly simple analyses actually in Flow3D. Also hydraulic jumps, all those sorts of things reveal themselves nicely in 3D with 3D CFD tools. Okay, I wanted to actually talk a little bit about PK-wares, just because we've been doing quite a bit of work on this. PK piano keywares are being used more and more all over the world, Asia, Europe, United States as well now, South America, and we wanted to see how well these Flow3D performed for this type of spillway capacity analysis. So we've been doing a bit of validations on this, and so far it looks very good. This is one of the runs I just got back recently. We have basically perfect alignments. The red dots are the Flow3D results, and this is experimental data from Ricky Anderson's thesis at Utah State. And in fact, we'll be presenting this. Well, we have a poster session and a paper at the USSD National Conference in just a few weeks in Anaheim. So if you're around, step, come and see us. What does it look like? This is the video, the animation of the spillway is coming this way or this way in this view, and this is a slice so that you can see like a cut of what's going on over the edge here, and the kind of this is assuming it's aerated. It's important, and then we can get some kind of insights into the this is a cross section sideways of the structure. All right, so much for kind of complex free surfaces. I think you get the picture what can be done and how it could apply to your problems. For open channel flows, it tends to be a bit less dramatic, and what we typically after are velocities, pressure, elevations, and the operational effects of turning pumps on, discharge structures, opening discharge structures, opening gates, and those sorts of things. So this is an example from the New York Power Authority, NYPA. They gave us a nice talk a couple of years ago at a conference, user conference, and what you should see here is these are the streamlines. This replicates the geometry here of this area of interest. Okay, so those sorts of things, reservoirs, rivers, waterways, and at this point, probably 10 kilometers is the kind of scale at which you can still do things in 3D for 3D solver fairly comfortably. Above 10 kilometers, it starts becoming a bit iffy in terms of hardware. And what we're looking at here is a discharge. This is the power plant. This is actually a tracer, and we're looking at where does the tracer go as it leaves. So how does it disperse? There's recirculation regions. There's all sorts of interesting features if you look at this in detail. But the point here is that on the open channel side of things, with 10 kilometers in full 3D is kind of where we are. Of course, it's always expanding because hardware is improving all the time, but this is kind of my rule of thumb for now. Beyond that, we switch to shallow water models, which we have in Flow 3D as well, but in the 3D case, we stop around 10 kilometers. Okay, so what I've done, in fact, in this presentation, I've kind of dispersed multiple links to papers. So if you download this, you can just click on these links, papers of interest in different topics throughout the presentation. So in this case, they are trying to, this is by Michael Skurlock and some colleagues, and they were looking at trying to reduce the velocities on this side of the channel here by using training structures. And there's all sorts of choices to make, all sorts of design parameters that you want to evaluate. And CFD tools are a great way to do that. You get a full 3D picture of the hydraulics, and you can move things around and rerun things very quickly. So very useful to see how structures affect the flow, and in turn, and this is all with the goal of alleviating the erosion on those embankments. This looks like an internal flow, but it's not. It's a flow splitter, but it's open channel. And what's happening is the flow comes in through here and is split through these three containers here, and then there's a weir exit here. So weir flow. And the question is, the first question is the structure splitting the flow evenly? So not quite. In this case, it's close, but it's not perfect. And then other questions are, in terms of grit, where does the grit deposit, where does it go? And for that we use additional models. But you can still get a lot of information about your design just looking at the hydraulics. And then internal flows, we don't do an awful lot of those, but it's completely seamless within Flow 3D. We tend to focus on free surface problems, but internal flows are there too. This is a static mixer, and we're looking at how well this scalar here is mixed as the flow goes downstream. The idea of this plate here is to create a lot of turbulence and recirculation to mix the fluid as well as they can. All right, but a very common situation is in fact a mixture of pressurized and free surface. Okay, so in this case we have a pump here that's pushing water through the system, goes down into a culvert, and in fact this is inspired from another case where we had a series of these structures with multiple pumps. But what we have here is a region where this is pressurized and then this is free surface. Okay, but it's completely seamless in the way we do things in Flow 3D. So there's really no added complexity there at all. Okay, and then this is another CSO example, generic, but it's got some interesting features. First of all, this will pressurize, so we're going to continue feeding flow into this until it pressurizes, and in fact, so this region is pressurized. This region, because of the geometry, in fact never pressurizes, and then we have some weir flow up here. So you can see, you can learn a lot of the behavior of your structure for different flow rates, different storm surges and so on, and see when, at what points you will have discharge, which is presumably what you would like to avoid. Okay. And different, but an interesting problem that came across my desk a couple of years ago. This was the McLaren Dam, and there was a rapid shutdown of the turbines, and a significant flood wave propagating upstream and caused a lot of damage. And normally you would you could quite simply run this with a shallow water model. It would run very quickly, but in this specific case, this is a log barrier, and it's a rigid structure that actually goes underwater. And so when the wave propagated back from the turbines, we're going to see the turbines shutting down in a minute, and we can see the wave propagating up. They get pressurized, in fact, under this structure here, and then make their way out and upstream. So that pressurization, if it's significant, in fact, makes the shallow water model non-valid. You can't use it in those circumstances. So there's one case where I thought it was quite interesting to have a 3D solution to look at the pressurization of that pulse as it moves upstream. I have another paper here, which you're welcome to take a look at. It's very interesting. It's some work done in Karlsruhe and University, and they do a lot of fishway passages. And what's nice about these types of simulations for fishway passages is you can get some very good detail into the recirculation zones, the turbulence intensity, the velocities, all of that. You get an awful lot of information using CFD tools. And it's been used a lot for this application. And in fact, we had a talk a couple of I think 2015, yes, 2015 in Denver. The USBR presented at a user conference, and this slide was, I thought, completely fascinating. It gave us kind of an insight into what they've been using. They've been doing CFD work for forever, since I think '94, and they've done all these. Just a lot of projects, very cool projects, a lot of nice reports. And but when you look at this list, you have a lot of fishway passages, fish bypass, etc. A lot of reservoirs, pumping takes, spillways, a lot of spillways. I thought so. It's just an interesting list to see what people do over almost 2 decades actually. So. There you go. And the last one here, spillway vortices. I think in 1997 they probably had some difficulties with the computer hardware at the time, but now we can get quite good. So speaking of gate vortices, there's something called a Q criterion. So this is a spillway here, and we have a gate and the piers, and what happens is vorticity is generated around these piers, and it can be significant enough that you actually have void opening all the way to the gate. So some danger there, and there's a type of analysis called the Q criterion analysis, which is just part of the regular post-processing we have, and that gives you, it identifies coherent vortices, vortex structures within the flow. So you can see nicely here these multiple vortex structures that are originating from this pier. So you can see a little bit of the depression at the free surface, but really the good information is to see where those vortices propagate in a domain. So in this case, we expect it to be here, but it's not always the case that you know ahead of time where vortices will develop. So a nice tool there for people working in this field. Okay, so I've spoken about 3D, free surface, pressurized. A lot of things can be done with shallow water models. So in this case, we looked at this a couple of years ago, and this was validation for the St. Francis dam breach. And what happened is a catastrophic dam breach. This scale is about I think 80 kilometers, sorry, and goes from St. Francis Dam to the Pacific over in California. So we did there's a paper on this as well, or a presentation rather. It's nice, but so we looked a little bit at everything. We looked at 3D solutions, and we realized that really this, so in this case we modeled the first 5 kilometers of the breach in 3D, and that was already quite challenging at the time, but you can do it. So this is a 3D, so this is the portion of the wall that did not break. The rest of the dam breached catastrophically, and this is a 3D simulation. You're going to see the super elevation here, the kind of banking around the domain. But that's a 3D solution, and that has limits. There's no way you can do the 80 kilometers in 3D. So that we were interested in looking at that. And what we can also do is, in fact, do the first portion where the vertical accelerations are expected to be quite strong. We did that in 3D, and then the portion that's in blue here is in shallow water. So it's a hybrid model. It's one model within Flow3D, but it's hybrid, where you say, well, this region, let me just go back to the beginning there. This region, we're going to do a 3D analysis. And just by the way, this is a 40-foot tall wall of water breaking through here. And then we switch to shallow water. So this validated very well. The difference, it's not on this graph here, but the difference between the hybrid and the shallow water version, the timing of the wave was impeccable. This is about 2/3 or 3/4 of the way down to the coast, and the timing of the wave was bang on the money. But the difference between the hybrid and the shallow water solution was that the hybrid, in fact, showed a higher wave elevation, and we don't have real data to calibrate the height, only the arrival. So we don't know exactly, but it was interesting that we had a higher wave crest here. Using the hybrid model. And then for 2D, I mean, for shallow water problems, there are a lot of codes out there, just dozens. And so we got a little bit curious and looked at how ours compared with the other results. And in fact, there's a validation here that's been, or a comparison that's been done with all these codes. It was done a few years ago. So we looked at this data set, and in red is us, and so it's good that we are basically on top of everyone else, just not better, but just kind of the same as everybody else. So that's good in terms of verification and validation. Okay, so the key of what I've said so far is that a lot can be learned looking at the hydraulics only. We can do an awful lot of things across all the many applications, municipal, dam, rivers, environmental, just looking at hydraulics, and those are some of the simplest things you can do in Flow3D. So that's good news. These free surface problems are ubiquitous, and Flow3D is just a tool that's simple and accurate, robust, all those things for those types of things. And when you're looking only at hydraulics, and I can tell you because I've been doing this for a while, really, if that's all you're doing, hydraulics, and it's really a straightforward setup and procedure in Flow3D to get those going. Okay, and in fact, for many applications, you don't even need additional physics because the fact of the matter is it's all hydraulics, and so you can leave it at that. Good news. So what's the workflow? For us, it's, and for most packages, I'd imagine, you start with your geometry, and that can be either your CAD, 3D CAD, or it can be terrain, from GIS or whatever. So for us, we import 3D CAD in the STL format, which is a really quite universal 3D CAD solid format. And for terrain, we use the Esri terrain, quote unquote, ASC format. We don't use that's a ASCII, anyone can read it, it's universal. You don't need any special tools to open and obtain that kind of format. And of course you can have, and that gets imported directly, or you can mix things, of course. You can mix CAD and built infrastructure with terrain, or you just import your data, import your CAD, import your models, and it just builds an environment within Flow3D. Then you would choose some basic physical models. So for water, just water, it's basically gravity, viscosity, and fluid. Those are the only models that you use for straight hydraulics. Meshing step is really quite trivial. You place a box around your structure. Sometimes there's a bit of refinement in different areas, but that's not too difficult. And then we have initial conditions, where is the flow at time 0, and then boundary conditions, what's happening at the boundaries over time. So those are important to, you need to have a handle on those. And then you select what you want to measure, what you want to get out of your simulation, and then you analyze your results. And we have a tool there called FlowSight, which is very powerful. It helps a lot. So you'd start with some kind of structure from your CAD. You would, as an example, you would import that into Flow3D, and then sorry. What you would look at then, in this case, let me pause this, what we are doing is we've defined some water at time 0. This boundary here is just an outlet, so flow can leave. This is a weir, this is also a weir, and that's also a weir. And we have flow that's allowed, I think we have an elevation on this side, and then an outflow on this side. Flow is just allowed to leave. And then at the entrance here, we have a fluid elevation that's increasing with time. So you're going to see how that works out and propagates into the domain. We have first a weir flow, and then, well, I'll let you see, we have 4, this is a high flow rate. So we are at the limits of what this structure can handle. So we have flow coming in, and then flow comes out this way, and some of the flow is diverted on this side. Okay, so if you, well, you can see the flow coming out over this way, the flow coming out on this side, and here we have a tracer just to see, for this, you can just to see what's happening to the flow here. Tracer is always useful to look at where things are going. Okay. So again, the creation of the CAD environment, that's really fun. Before you even open any kind of CFD tool, you need to have your CAD created, and that's not a CFD job. That's something that is done in CAD software. So the creation of the CAD environment is very important and can be time-consuming, especially if there's a topography or field data that you need to kind of integrate. Determination of the physics and flow environmental conditions. Typically that's the hydrography. Or hydrology. So that's a key that can take time as well. What's important? Is it just water, or do I need sediment? Do I really need sediment, etc. So these are kind of questions that you determine ahead of time before you open Flow3D, and then you bring this into your CFD analysis. This is a whole topic unto itself, but verification and validation is hugely important in CFD work. So especially if you're going to do this kind of on the long term, you need to have methods and procedures in place and it's only with those procedures that you can actually get actionable insights. If you do CFD analysis without this part, you do not get to this part, the insights part. It's too much risk. So it's important, and there are plenty of things that are well documented, and there's also plenty of methods and tools, but I won't go into that today, but it's very important to be aware of that. Okay, so more details. I've been through these hydraulics kind of quickly because I want to also talk about other topics, but there are other presentations, and if you download this presentation, these are all links to previous presentations. But they don't show you, how to do it technically. So what I did is to also create a couple of video tutorials. I have more, in fact, but those are A to Z tutorials where I show you, the graphical user interface. I show you the software flow 3D, and I go through all the steps and just describe what I'm doing. They take about 10-15 minutes, and that shows you exactly how it's done in practice. But that part is not really what I want to do in these kind of webinars. I'm more interested in kind of what we're doing. Not so much the how. So these tutorials, I encourage you to take a look if you are interested. And then more technical, conference proceedings. You can search conference proceedings, and there's also a bibliography. It's all on the website, but there's just a lot of information. And if you just search topics of interest, things will come up usually, and then you can read what other people have done. And then we also have our own technical notes. There might be, but I don't think they're on the website, but email me if there's a specific topic of interest. I'm happy to dig those out. And I just noticed a spelling mistake here. Okay. All right, so I spoke about the hydraulics, this one, open channel, mixed open, pressurized, internal flows, all those things. I will now address some other topics. So take a sip of water. Okay, so sediment, plumes, gas, bubbles, all those things, all very, very interesting. And let's start with sediment. So we do, what we model, first of all, we model cohesive, non-cohesive beds. Cohesive is a whole different beast. And so this model is for non-cohesive sediment. So we model the settling of suspended sediment. We model the advection. The suspended sediment is carried with the fluid. We model the entrainment of the sediment, so it's pulled off the bed and into suspension. Some of it is advected, some of it settles back and packs again the bed. And then we also have, as a transport mechanism, we also have bed load transport and all this. And we have two states, basically. We have suspended sediment or packed sediment. So we do all that, and then a few more things, angle of repose, Richardson-Zaki, those sorts of things. And this is, these are based on empiricisms, the critical Shields number in particular. But altogether, it works fairly well if you have a grip on an idea of what to use for Shields numbers and those sorts of things. So we can do multiple species. So you can have the diameter for different sediment sizes, different densities, and then you can mix and match them, and you can create a substrate which has, say, 50% fine, 20% coarse, 30% medium. So you can create your species here, you mix them all together as you want to for your actual substrates. Okay, so what does this look like? Typical, flow around a circular cylinder. So we have the free surface, which has, and then we have the kind of vorticity structure here that happens behind the pier, and this creates these regions of scour as well as deposition behind. So it starts with scour there, and I should have probably let this run a little bit longer. But so these develops very typical patterns with some deposition in the back. And of course, what's nice is that you can choose all sorts of configurations once you've validated the basics of what's going on in a well-known case. You can move on to more complicated geometries, plunge pools or multiple piers and those sorts of things. Okay, so talking about, I think I showed you this earlier on, just the hydraulics, and when we just had the hydraulics with a solid substrate, this would just make its way down. If you recall, there were completely different hydraulic patterns there. What's happening with scour is that you dig a hole here, and you can see it here from the top, and here from the side, and then eventually there's enough water in here that the shear stress at the bottom here ceases to erode the bed, and you get this kind of equilibrium plunge pool behind the jet. So that's what we're after, the size of this and the location of this hole, and possibly the deposition behind of sediments, of course. Okay, so as a matter of validation, there's a fairly famous experiment called Chatterjee in 1994. So what's happening here is we have a jet coming out here. This gate here is in fact this position, and then this is a solid slab, and then we have erosion and the coupling of so a change in the bed shape and the coupling with the hydraulics and equilibrium eventually. So this was an experiment, and let's see if I jump this. Takes an hour, so this is the final shape after 3,600 seconds. And this captures, this is a great validation because it captures entrainment, bed load transport, packing, angle of repose. It captures all those things, all those mechanisms. And they're all important to the solution here, and we want to make sure that we are able to reproduce this, which fortunately we are. So this, you can't quite see probably, but the calculated is flow 3D, measured is the experiment. So we're doing pretty well. This is the dune height, this height, and this here is the scour depth hole. So we're doing pretty well considering the complexity of this process. A paper here, which was brought to my attention just a few days ago. It's very interesting. So it's exactly this problem. Plunge pool looked at with 3 different perspectives, one of which was a flow 3D scour model. So I thought that was interesting, and here's the link to take a look here. So we have the pool here, and the question is, where are they going to? They're going to build some remediation here, and where to do that, because there's a lot of construction involved, etc. So they're able to get a handle on the scour and the depth and all those things, the location, all those things. So and then combining this with 2 other methods, which basically all point to the same outcome, same result, gives you extra confidence that you've performed a correct analysis. Okay, and then here's another one, which you're welcome to download. Interesting. This paper is actually trying to specifically validate flow 3D, so I was quite happy that it worked out pretty well, in fact, for this problem. This is from, I think these guys are in Zurich, if I'm not mistaken. I should have mentioned that on the slide. I think it's ETH. Okay, and then I had to show this because it's I've never actually even seen this before. This is actually a turbine that's activated by tides, I think, and so this turns. There's some vorticity that goes behind. There's the tidal signal on the pier itself, and they're looking at the scour behind this structure. It's really quite cool. So that's another reference. Okay, so it's not all scour. Sometimes we're also looking at bigger scales, and we're looking at sediment transport, not the scour, but just the entrainment and transport and deposition. So we can couple, for those larger scales, we can couple sediment transport with a shallow water model instead of doing a 3D analysis. If this is a long river, we would use the shallow water, but it works completely seamlessly with a sediment transport model, and we can see different results, different concentrations for different sizes of molecules, non-molecules, particles. In this case, this is showing the 10 micron range. Right, so thermal plumes, I like to show this slide because it shows kind of the mixture of, this is warm water coming in, so it's a jet, so but it's warm water coming into a basin. It has some kind of features associated with momentum plumes, but it's also lighter than the surrounding field, so it will, first of all, the buoyancy will participate in the turbulence, but also the water generally will rise upwards. But then we've added particles of different sizes, and you can see the heavy ones. This is via the sediment scour model. The heavy ones just basically drop right away. They're too heavy for the flow to really entrain them. The intermediary sizes, some of the particles are able to make their way out, and then the lighter ones, 100 microns, they just basically follow the flow. So these are the dynamics that are come into play in turbidity currents. And what's nice today is that with computational power, we can do both the near fields and the far fields for these plume problems. We can do those together. We don't have to separate them like we used to have to do the near field and then a separate simulation for the far field. We can do those things all at once. So good. And if you look at a larger scale, we can now, I forget the scale here, but it's order kilometers. We can have your plume coming out, and then the detail, in fact a lot of detail about the regions of where you have warm water. And you can place probes. So there's a lot of post-processing you can do that's very, very useful into giving you insights about what's actually going on at different locations in the flow. Okay, and just as an example of post-processing, in this case what we're doing, this is a plume as well, but on the lower here, what we're doing is we're coloring the bed, the riverbed by temperature. So this is not about the fluid, it's about where does warm water impact the benthic community in this area. Okay, so that's, well, I thought it was a very interesting way of looking at the temperature signature, not just in the fluid, but on the riverbed. And for turbidity currents, I'm going to reference this paper. Really great. The river storm inflow basically plunges down, and so the water seems to be clear at the surface, but in reality what's coming out is very, very dirty and full of sediment. So they were trying to model this, and I'll just show you some results here between field data and numerical results. It's really good. Same here with the turbidity. And there's some other slides there with the temperature in there, which I don't have here, but they are in the paper. It's a good example of this kind of analysis. And very often, coupled with thermal plumes, you have where you have an outlet, typically it's because of a power plant, and you have an inlet somewhere, especially for once-through type power plant. So one of the questions for fish is where is the flow at a certain threshold velocity, and volume rendering is in fact a great tool to show you where the flow is greater than a threshold velocity. So this blue region here tells us where is the flow greater than 1 meter per second. That's about 3 feet per second. In these regions, and the flow is going into the pump here, in these regions the flow is greater than 1 meter per second. So you can do all sorts of thresholds. It's very interesting. These are the streamlines, and this is a view from downstream. Okay, so so much for that. I want to talk about bubbles a little bit. It's a new model in Flow 3D. What's happening here is we have gas bubbles. We used to have mass particle bubbles, mass particle particles. Now we have gas particles, and so they have buoyancy, they have size, and they are fully coupled with the surrounding flow. So what happens is when you have a jet of bubbles here, it entrains, in fact, the water around it, and that's why you have this recirculation of water and this plume coming up and pushing up a little, bubbling up at the water surface. So that's a very interesting new development, very relevant for aeration tanks. This is an example here of a circular one, and you have bubbles coming up, and then this recirculation that's being induced by the bubble motion. Now, you can also apply this to larger scales. It's a very efficient model. Computationally, it's not a problem. This is vastly accelerated. That's why it looks a bit crazy, but it's a large-scale lagoon. And what we're looking at here is the fluid coming in here, making its way through here, and then back and back. So it goes like this, generally speaking, and we have the interference between the bubbles, which are supposed to keep everything both aerated and suspended, and the actual flow. So these all are coupled. And you can easily add mass particles to this. And this is an interesting example here where we have the kind of brownish particles are gas particles, and these here are mass particles by different sizes. This is 10 microns, this is 100 microns, this is 50 microns, and this is 1 millimeter. And again, the heavy ones tend to sink and cannot go anywhere, whereas the lighter ones are able to make their way out. And understanding what can do what based on the kind of energy of this motion from the induced fields from the gas bubbles, and how smaller mass particles relate to this is of key interest for many of these applications. And this is the same thing, but I kind of wanted to show you, just separated into two particle sizes. You can see how the blue particles, the lighter ones, are really stay entrained, whereas the red ones, which are heavier, kind of sink down and are not able to be lifted up by the induced current. Okay. Related, air entrainments, many applications where air entrainment is really important, and spillways. You look at this, and of course, it's impossible not to think that air entrainment must be critical to what's going on here. So, worth looking at that in detail, and we have an air entrainment model just to show you basic simple simulation here, but one is with air entrainment and one is without. And what you can see is that in this case, there's no air entrainment, and the water basically kind of makes its way out. And this is a recirculation zone. If you have air entrainment active, the bubbles have an effect on the flow itself, and you can see, in fact, drag the flow upwards much earlier than it would otherwise without the effect of air entrainment. So you can see basically the velocity here. This is with air entrainment, this is without air entrainment. It's very different because this air basically wants to come up to the surface, and in doing so drags along the fluid. Okay. And for this case that I had shown you earlier, I showed you just a picture. What's happening here is we have air entrainment that is so pronounced that it basically creates a pumping action up and down, and makes the whole structure unusable. That was a very interesting project, and there's a full definition kind of explanation in this previous presentation. You can click on that. And then finally, we have a new development with our air entrainment model. We now have a dynamic drop size. It used to be that we had a fixed drop size, which is not very physical. It was a start, but it wasn't very physical. And so in the air entrainment model now, we can the size is dynamically changed according to coalescence and breakup based on turbulence and a couple of other parameters. So there's a paper on this validation, but it's really good. We have some data from again from Zurich, and we're able to get some very, very good results there. So that's an exciting development, because a lot of work is happening right now, multiple institutes around the world on aeration of these types of spillway structures. Okay, and conversely, you can have siphon or negative pressures build up. So this is what I showed you earlier on with just no hydraulics, just pure hydraulics rather, no air entrainment, and no pressurization of this valve, of this is evolved, but no pressurization of this void. We can also pressurize voids in Flow3D. So when you do that and you include air entrainment, things can become more realistic, and I can tell you that this is in fact a real scenario that did actually happen, something very similar to this. And what happens is you have this kind of choking, and you can have violent behaviors because of the basically because this void here becomes depressurized, in fact, is what is happening. And it doesn't happen, it only happens in certain specific flow conditions when this gets basically trapped and removed from the atmospheric. There's no pathway here from this void to the atmosphere. So different behaviors, and it's really amazing how often you see behaviors with air entrainments that are quite different from what you'd expect from the pure hydraulics. And this is seen in real-world applications. Last thing on particulate dynamics, I think, settling tanks. In this case, we use a slightly different formulation of the sediment model. This time the settling velocity is based on concentration rather than drag and those sorts of things. It's much more realistic and you get good results. Then there's a previous presentation that focuses on this as well. And for this one, finally, a vortex chamber. So the large particles tend to go out through the bottom here, and you can see in this central vortex, the lighter particles escape through the top, and you can measure exactly what's leaving of each particle class, each particle size. Some are leaving, some are leaving through the top, some are leaving through the bottom, and you can differentiate between particle sizes. So you can makes for fairly precise design based on what kind of particle sizes you're trying to remove and which ones you're trying to keep, based on the flow rate and all those things. Okay, you can see here all the central vortex here, these leaving through here, and the other ones leaving, the heavier ones leaving through the bottom escape. Okay, so chemistry a little bit. Very straightforward actually, just put in your kinetics, and in this case we have just the chlorine is injected. This is just a test, very common test. You put a pulse of chlorine and see what comes out on the other end. And then you can couple this with biokinetics. So the chlorine can react with an organism, and at the entrance of the structure we can have, say, 1 million organisms per cubic foot or whatever, cubic meter, and then how many of these organisms, what has been removed by the time you leave. And in this case it's not 100%, it's 90%, and so on. So you can couple the kinetics of the chlorine decay just with time and water, and with the reaction with organisms, and consequently the organism decay, and that's coupled with the hydraulics. So that's a common application. General moving objects, just a couple of examples just to show you how these things move around. This is a mixing tank. This is 2 paddles rotating counterclockwise. Well, not counterclockwise, but counter-rotating. And yeah, it's not a very complicated simulation. This one is quite splashy, but it's because they're moving quite fast. And with catenaries, and we can couple those with floating, with GMOs, which are moving objects, and we can look at floating barriers and how these things behave under a wave train, or so these are or currents, and these are catenaries, floating catenaries. These are floating objects, and they're all coupled together, and with and these are moored to the bed here and there. So we can see how these things move, or we can just have a catenary, and in this case we have these 3 pumps here which are going to be cut off one by one, and this is just one floating catenary, but then you can get a broader picture, a broader view of how these things are going to move and what velocities they're going to be subject to under different operating conditions. So in turn, this influences, of course, the design of how strong these barriers need to be when you have strong strong flows. Okay, and then the last topic, briefly, it's been just about an hour. So we can have, not everything is made out of water. Of course, we can vary density, viscosity, those sorts of things when we're doing an overland spill, if it's oil or any other fluid, not a problem. This can be shallow water or 3D. And then an interesting one here is bitumen, in which case naphthalene evaporates. And as the naphthalene evaporates, the density of the fluid changes. So as this is spreading out, there's an initial phase where naphthalene is evaporating and the density of the fluid is increasing. And then once there's no naphthalene left, it's just pure oil there, and so it doesn't. There's nothing left to evaporate, and the density stays constant. And in fact, the same thing happens with the viscosity. While this is happening, the viscosity is also changing. It's not shown on this, but it's part of this. So there's phase change and also dependency of viscosity with, in this case, I forget exactly how it's with the naphthalene content. Okay, and then Bingham plastics. Well, it could be anything, but many fluids are not, in fact, Newtonian, especially when they become cohesive soils, as a case where you have distinctly non-Newtonian behavior and where the sediment scour model completely collapses. So for cohesive soils, in this paper, this was a user conference, but what they used and had good results was with a Bingham plastic to model this cohesive soil here. So that's it from me. What I kind of hope to have shown is that Flow3D offers a vast array of modeling capabilities, which are kind of all relevant to various aspects of the water and environmental industries. It's a modeling platform that is both powerful and versatile, and I can tell you also from extended usage, it's a modeling platform that's frankly quite easy to learn and to use. And so I will leave you with that. If you have any questions, do not hesitate. Email me at john.wendelbo@flow3d.com. And a big thank you to all of you for attending. And if you were in different time zones, maybe you will watch the recording. Thank you as well. Until next time.